Good morning. This is George Laird talking, and I also have Adrian Jensen on the line.
Good morning, everyone.
Oh, good. You're there. Excellent. So we're the technical side on the CAE for Applied CX. We're predictive engineering, and we do the technical support, seminars, and we also have consulting services. And for a lot of you guys you've been to our seminars. These are technical. We don't get into marketing. There's no hook. There's no bait. There's not like you're going to see this great stuff and then you have to buy something. Nope, nope. What we're going to do is we're going to talk about thermal stress. And everything you're going to see here is within the base package of Femap and NX Nastran. So we're going to go through very lightly on the theory, and we're going to talk a little bit about our experiences, not too much, don't want to bore you guys, and get into actually running a transient analysis. Adrian's online. He's my senior staff engineer. Should have done a little more introduction. I'm the principal. I have a doctorate in mechanics out of Oregon State University, lots of years of modeling, and Adrian has a bachelor's out of Oregon State, just by coincidence, sort of the way it worked. Same university, and going on 6 years with predictive and hundreds of projects that he has done. Okay, he's going to be online. He's going to be able to answer questions that come up. So on your panel in these GoToMeetings, if you have questions, just go ahead and type it in, and he'll get to them. If you can't get to them, we'll get to it after. We'll get together. Okay, we like to make these punctual, get it moving, and make sure that you guys can get out of here on time. So this is what we're covering, and this white paper will go out. It'll get posted to the Applied CAX site under technical seminars, and we have a lot of seminars there. And it'll get posted after this, and also be the recording. So I don't want to be redundant, but here's an outline of what we're going to cover, and you can, I would just say you guys can read it at your leisure later on. So this is what we put together to announce the seminar about why people might be interested in attending. Okay, what do we know about thermal stress analysis? Lots of variety, from LOX and rocket fuel tanks, transient thermal analysis, liquid nitrogen, liquid oxygen, composite curing mandrel, which is common in the aerospace. As you make these aluminum mandrels, you got to heat them up to cure the composites. A little 500 kilowatt generator turbine. They use bypass air, and it spins at some insane 50,000 RPM frictionless bearings. A little solar panel converter, lots of thermal stress, and expands. There's silicon potting compound, expands, pushes things around, tears the chips apart. ASME tube sheet. This one was, we're going to actually use this for our transient thermal analysis. It's a thrust collar on for a hydroelectric dam generator. More electronic components. This is active optic cable for space use. This is a telescope, plasma tube, brazing, electronic components. Well, this is a what is it? A high voltage blaster for an X-ray device. Old school stuff: thermal stress analysis on a water-cooled furnace grate, plates, transient thermal, electron beam welding, where you're doing residual stresses. This is LS-DYNA. Hydrogen reactors, tubes, hydrogen, porous membranes, thermal stress in Kevlar carbon laminate. This is really fun. This is probably the simplest analysis you can do. You just put the layers together, you give them different CTEs, and you run it. You give it a delta. And this was for some underground piping with thermal analysis and stress, because things were breaking and cracking underground. So thermal stress or thermal deflection, it's all the same. What you're doing is you're creating strains in the part by a delta T, and it can be steady state and it can be transient, it doesn't matter. An equation is so beautifully simple. I mean, you have a strain, and that's equal to your coefficient of thermal expansion times your delta T. That's it. I think everybody has seen this, and it's sort of boring. You know, it's all there. But the actual application of it, that's where sort of the devil in the details of getting down into it. So we're gonna go in and do some application work. because in theory, you're creating strain. The strain is your mechanical load. That's your mechanical load, is strain. So sometimes when people think of thermal stress, they say, oh, you're doing a thermal analysis. No, we're not. I mean, that's just, only thing we do a thermal for is to create the load case that drives strains as our load. And since it's FEA, F equals KU, we know that strains get converted into equivalent forces for the actual analysis. So, okay, we're going to use a B model because we want to just keep it simple. And we're going to use these two sort of unusual materials. We're going to use alumina and what was my other? I think it's stainless steel for the two materials. So, and we're going to set it up very simple. We're going to say that our reference temperature on the material card is 0, and then on the body load, that we're going to raise the whole system up 500 degrees. So we're saying, this is the logic I like to use, is that your material card is saying, that's your material, stress-free, everything, happy-go-lucky, that's your temperature. And then you can use a body load, and this is for all systems. And I'm going to show how to do it for individual parts. There's lots of flexibility, but this is just, coming out of the gate. And our physical analogy is that we have a structure, we heat it up to 500 degrees, uniform temperature. We don't, and it's slow. There's no transient effects. It's slow, rise at 500 degrees. We want to see what happens to it. Okay. The two models I've chosen are just give you an example of what happens when you apply strains to a structure. And if you don't have any constraint, it can just expand. I mean, there is no stress. I mean, that's sort of, it's one of those things that, and I mean, it's obvious, but there's nothing like seeing it in a model. And I'm using the new Femap 11.2, and we'll load it up, and there's our model. And we have our two materials, right-click, edit, reference temperature 0, loads, temperature, well, here, I'll go and expand it. I should get down, body load, right-click, edit, 500, done. And then that's our load. And, I mean, it's just a static stress analysis. That's it. Nothing fancy. And you can, I already have the result set saved. I don't know why I hit analyze. Force I have it.
Hey, George, you mind bringing up the body load one more time? There was a little bit of lag looking at the body load.
You bet.
There we go.
Good.
Yeah, just so people get a chance to see where to stick
body
that.
Load. Yeah, I know. It's like, how do you do it? What's the actual gig? So we have expansion. So you might notice too, we have our own color scheme and background scheme, and we really don't like the default Femap. And well, it's art. Everybody has opinion what they like, and so anyway, if you guys want tips on how to arrange all your colors and stuff, we're happy to dive in. So we're looking at, you can see the displacement on it, and if we turn it off, there, of course, it goes back and turn on the deformed, and that's real logical, but you have no stresses. It expands, but you have no stresses because nothing is constrained. Now, on the second example, like this, we have our alumina welded onto our stainless steel bar. Same scheme, same delta uniform temperature. Now look at both. Now look at that, 85,700 stress, lots of stress, and the deform. You can imagine what's happening is that because they're linked together and that they have different coefficient of thermal expansions, they're going to tear themselves apart. And that is where typically people, the reason why you want to do a thermal stress analysis is that you have different materials in your structure, and they're going to be heated up. And so these different materials with different CTEs, it's a very powerful load set because it just creates huge forces. It creates the forces. You have a strain, And the amount of stress is dependent upon the elastic modulus of the material. So thermal stress is one of the most, I don't know, scary, dangerous, intriguing load sets you can get because you can create such high forces on your structure on it. So that's our two intro, and then we got this other one. Just I wanted to talk about a little bit more constraint, and this is just, and I think it's sort of obvious as you see it. You got your part up here, and here's your bracket. It's just pinned down here. When you give it the body load temperature, just clean 500, this is going to expand. It's going to push it apart and create stresses down here. You have constraint. If you don't have constraint, you don't have stresses. So there's on the thermal stress, you look at different CTEs and constraint. Adrian, did I miss anything?
I think that's good. No, I think these, and for anyone that's getting into these problems, this type of model is exactly what you want to start with. And, you know, George and I do it. We recommend everyone to do it before you tackle your big assembly. Build something with some beams, just a few elements, and sort it out like this. It's very insightful.
Yeah, it helps you know what you want to know. And then, of course, you got to do a shrink fit example. I mean, that's classic. Everybody talks about shrink fits. So I don't know everybody, but at least that always seems for the training, you know, the standard. And I want to introduce the use of contact on this shrink fit, because there's one of the things you can do is what we're doing is, okay, what is the physical scenario for this? Well, the physical scenario is saying, okay, we're taking the pin and we're dipping it in liquid nitrogen and we're cooling it to 200 degrees C. Then the block is heated up to 200, you know. And even given those crazy temperatures, they're saying, well, just because, you know, the pin is still sized for the radius, you know, 25 millimeters smaller than the hole in the block. Okay, so, you know, it's given a slight little different in sizing. And let's just say that the other thing, when we built this model, we just built the pin with the same diameter as the hole of the block. You know, it allowed us to get a matched mesh on the geometry, because we just matched them up. And for doing contact, if you guys attended one of our contact seminars, one of them, because I think we've done several, you know that if you really want beautiful stresses on contact, match up the mesh between the master and the slave. And that goes for whether you're doing NX Nastran or you're doing, you know, ANSYS, Abacus, Elastina. They're all the same. They're using all the same under the sheets. So, so what I want to show on the model is, let's see what's the easiest way to go there, is that they give you this nice little capability under regions, edit, is that you can just tell it to give an offset distance right there. It's very handy. And then setting up that contact is just normal contact, normal NX Nastran linear contact. I gave it a little friction, nothing fancy. The analysis, and for our materials, what I wanted to show here is that, you know, of course, you could have one 200 and one 200 minus. And for thermal stress analysis, CTE, here's your elastic CTE. That's it. So, and the results down here, like that. And you can look at the form, and of course, well, that looks crazy, doesn't it? Because the pin, so we'll just go in, blank it out. Then you get this beautiful looking picture for your quarter symmetry. Well, of course, because it's a demo model, of course it's going to look beautiful. Okay, thermal analysis, setting up a thermal profile to use as a load case to a structural model. As you guys know, you can make things look so simple, or it could be just brutally difficult. In our work, we have mapped thermal profiles from static and transient CFD simulations. That's quite common. And one thing that's nice about thermal, to keep back in your mind, the thermal field is linear between nodes and between events. It's a linear field, where stress field is parabolic. And so mapping thermal fields onto structure with different meshes is really simple. You just use an interpolation function. I mean, it's just a linear function between the two. So interpolating this is really simple. And Femap, you can take spreadsheet data, you know, X, Y, and Z temperature, X, Y, and Z temperature, and you just bump it into your data surface. I mean, it's really slick, and most CFD programs will dump out, you know, X, Y, Z and temperatures. So not a big deal. And then we've also done, you know, electron beam welding simulations and phase change and residual plastic strains, and that's that gets a little more difficult. But so there's lots of ways to get there. If you come up with something, give us a call. We're happy to spend a few minutes and give you our thoughts on it. No big deal. Of course, the seminar, we're going to keep it simple. We're going to talk about uniform temperature. In my experience, that's been the most common. You're just heating something up. It's got a delta T, or let's talk about the reverse. You're doing a brazing of a couple components. So the reference stress is 0 stresses at the braze temperature. Then it cools down. Now welding, this is why people hate welding. Welding, your stress-free temperature is, you know, the pool is liquid, so everything's melted. And then as it starts to cool down, metals, of course, the elastic modulus will change as it cools. When it's red hot, the elastic modulus is quite low. That's what blacksmiths like. They can heat it up to red hot and pound on it. You get, you know, stress-free plastic deformation. So in welding analysis, you pretty much say that your stress-free temperature is 1,000 F or more, and you cool it to room temperature, and you get these huge stresses that come up. And so anyway, so this is what we're showing here, the two cards. Quick way to define fixed T. And then I also say there's an alternate way. We haven't talked about using nodal loads. Is that you don't have to define a body temperature, and you can set your reference at 0 and just use nodal temperatures on it as a nodal temperature load. Very simple. Now these simple models, we're going to have them uploaded to the seminar. So if you guys want to play with them, you can go ahead and play with it. Reference, no, that's the wrong model. I wanted no reference. I wanted this one, because here your load set is your nodal loads. Right here. Pull that out a little bit. Block, pin, and your material, you just set it to 0. Yeah, and no body load. Okay. And how am I doing on time? Oh, I'm doing good. Perfect. Let's talk about some of the more difficult scenarios of real-world modeling. And if you're building models of systems, not just a potato, not just one component, you're going to have lots of different parts. And that's just very common in thermal stress analysis, is that you're going to have stainless steel, you're going to have everything else, and you want to glue them together. This is simulating a braze assembly. And it's cooling down from a hot temperature, and different CTEs, you get crazy stresses. Now, we're using the Nastran glued connection setup. And this is one of the things that you got to be careful about glued connections, is that a glued connection is that it is putting behind the scenes to create that glued connections. It's putting in little rigid beams to map out to try to get the constraint correct between the mating surfaces. And nothing is perfect. And so what happens is that you can pick up on these assemblies where the meshes aren't perfect. You can pick up residual stresses. I mean, not even residual, just artifact, just bogus stresses. So what we're showing here on the top is your normal analysis, high stress. On the bottom, we set all the materials to the same material. I mean, it's the same material. And if with all the same material, you can't have any thermal stress. It just expands, it contracts, expands, contracts. It's all happy. Well, check this out. With the glue connection, you get a stress of 47 on it, and trust me, you can't get rid of it. We fooled around. We went in. You know, it's just part of the way the algorithm developed. So it's just something to note. Okay, what percentage of the total stress was it? It was about 10%. It was more than we liked, but it was just something we had to deal with, and we refined the mesh and everything else. But something to note about using glued connections. Now, this is one most everyone has probably dealt with this if you've done a thermal stress, is dealing with RBEs, or multi-point constraint equations. And if you know a little bit, we have a seminar on multi-point constraints, and they're beastly. Nastran is unique. They're the only code out there that's using MPCs. It's a linear code, and so what they're doing is they're making constraints. They're making equations between the stiffness terms in the matrix, and it takes into no account of the thermal. It's a constraint equation. So if you do it as a thermal analysis, I gotta show this model because it was fun putting it together. I borrowed it out of Adrian's FEA class. So, and the braze connection, we got models there, but they're sort of boring, and I'd actually like to make this seminar not run so long like everything else. So this is what you get with the standard RBE. And what we're saying here on this little model is that, let's go look at what I'm doing. So we're at reference temperature 0. Elastic modulus, Poisson, CTE. That's all you need, because you're doing strains. Strains is your load set. And let's heat it up, and I'm just giving it a body load. So we're saying stress-free 0, we heat it to 500. And we have it constrained on the back, Control Q. And there are constraints like that. And I wonder how many people have, I'm going to hit F6 and view options. I've been playing around. It's like, I've used Femap for years, and I never, you know, done things like that. Started using, oh, that's arrows, no labels. There we go. It's really cute, and I want to get the right color. Okay, there we go. Using arrows to define your constraints. It's a little easier to figure out how you're doing, so that's a pinned. So what's happened seems logical, I think, if you go, well, that's constrained, so it heats up, so the stresses just blow up. But here's your RBE element. And for many years, if people have been around using Nastran, you just groan and you switch over, use an RBE3, or you would switch it out and use beam elements, like a real beam element. You would map it out, use your to capture, not to have this constraint. Because I had to have drink coffee. The RBE element, multi-point constraint, is rigid. It doesn't know about thermal. So now you can rerun it, and this is one of the things I did. Is you go to modify, edit. I had to remind myself about the many moons ago when I did it. Is that you have to set your thermal expansion for the element, right? So you set that. You say, oh, thermal expansion. That sets it for the element. You can even pick from the material. They made it easy. You set that. You say, okay, fine. I'll just go in here and I'll activate it. Right-click, attach to results. Oh, I'm in the wrong. That's why. Here, activate. Analyzed. You think, oh, I'm home free. You know, I switched over the RBE, run. You think, and then you go, oh, it's still there. Well, the reason it's still there, and the reason why it's a little sneakier than you would think, is that you're actually switched the formulation of the RBE. The reason why you have to click there is because you're actually changing the element. It's no longer a multi-point constraint. It's behind the scenes. It's a bunch of beams. They call it a Lagrange formulation. You agree with the theory, but so they swap out multipoint. They change it to beams, and then of course with the beams all set, you can run it, and you get these beautiful stresses, which is right here. I put it. I already set it up so that like that. Voila. So there's a little thing about RBEs to make a note up when you have to get to them and you can't figure out why things are blowing up.
No, I've got one note on that.
Adrian, all clear?
Yeah, I got one thing to add. So whereas with the materials we get a reference temperature, with the rigid element we do not. I think it might use 0 as a default. So I think I've had certain certain scenarios
you're right.
where, maybe my starting temperature was, 70 and I wanted to go up to 200, but I would want to use rigid elements. So rather than going 70 to 200, I would just focus on the delta. So I'd start at 0 and go up to 130. So I have the same temperature delta, but you start at 0 to accommodate those rigid elements.
That's a good point.
Yeah,
I forgot about that.
because you don't get to pick a reference temperature for those.
Right now, or alternatively, you could set initial temperature to 70, and then do your nodal load to 200.
Yeah.
In the thermal.
Yeah.
And I'm going to show that in transient. In the transient analysis, you set the initial load, and you set the final node. But wow, yeah. Hours spent pondering. Yeah, and I want to say, and also too, that's why we're here in technical support. If you get something weird, don't, please just give it, don't feel you have to spend hours. It's okay. You can give us a call. We won't tell anybody. Anyway, so this is one of our more fun projects that we did locally here in Portland on a dam project. And so these are big honking generators, of course, as you can see. And occasionally they have to disassemble them. And the shaft goes down from this assembly right here. This is all covered up. You take the cover off, and you have the shaft, and at the end of the shaft is a propeller. And you got the dam head that comes through, pushes the propeller, spins the generator, generate electricity. So this is the thrust collar that holds on, that keeps the propeller and the shaft from falling down into the spillway and stuff. And it's shrink fitted on, and it got to be an interesting chase trying to figure out what was going on. To get the darn thing off, they have to heat it up. So they have guys running around this with blow torches heating the bejesus out of this. And so they're curious what sort of stress state they were getting from this torch heating. So it makes a nice little transient thermal analysis case. And what's really involved on it? And so I just put this down as a quick little workflow. And you create a temperature load with or without a time function. So, and you can have it just a temperature that says boom, it hits it. It'll create a little spike in your transient analysis, but you just run it out. You say, it hits it. You just run it to a certain time as it heats up. What's unique is you got to set your thermal conductivity and your specific heat for the material. And you got to ensure consistent structural and thermal units. We got a whole section on that, units. Then you run your transient thermal analysis, request outputs at desired time intervals, tons of output, convert thermal results into load cases, good luck with that one, and run static stress analysis at the end. So that's the workflow, but we're going to actually show you the details of how it is hooked together. So the images on the left here's our application of our temperature load, and you're looking at temperature. We're just burning it, and then we're taking that and applying it to stress. And I got the deflection turned on so you can see how it bulges out on that. So, but we're going to come back to that. Units, the bane. A buddy of mine, he does all this multi-physics stuff, and he says, I only use SI. I never touch any other set of units. And when I say SI, I mean pure, Newton, meter, kilogram. And I can understand that is, you know, you just get comfortable one set and that's all you ever touch. But that's not the reality. A lot of people out there have to use English units, and for example, unit sets of Newton millimeter is very common out there. I mean, that's like a standard. So you got to have some flexibility. So we put together this little conversion, and I like to work with, you know, I want to see the formula, I want to see how things are going, and then just how are the units put together, and then you just work on those base units. You take it back to the fundamentals, and I want to say, yeah, there's some clamor in, you know, the industry. Why are we still having to do this? Wouldn't it be better if the programs just do it for us and handle all the units and conversions? And yeah, and many of the programs do that. And I go back and forth. I've sympathy for it. At the same time, I don't know. It's a tough one. I feel there's, if you know what the units are, you're gonna have a better understanding of how to interpret the results. Yeah, you can do it with better confidence. Everybody's got their pro and con. So we're going to talk about using SI. We're going to convert it to our English system of snails. Now, slugs, if I heard of slugs, that's where you're dealing with your mass in units of pound force foot second squared. That's a slug. Got a foot unit of length. A snail is its pound force inch per second squared. So it's actually, yeah, Adrian's my master unit guru. So, so then we're going to show it for aluminum, and there's our little side-by-side comparison going through all of it. And you know, I think it's self-explanatory. Go through it. Now in Femap, they give you some default units. And the default, when you just come up with it for aluminum, they don't tell you what your thermal unit is in the default. So you're sort of keeping your fingers crossed and you're hoping that the CP is correct and the conductivity is correct. Just dangerous. I don't know. I just go from scratch, own your units. They do also provide other options for materials. So, and those are access. If you go to materials, go to new, and I don't know how many people, it's load, choose library, and the library is located. See, these are all the different libraries they give you for materials. So you got some choices that you can play around with. There's 3 here, and they're quite good. They give the units in very explicit terms. So, okay. So this is, they tell it is in BTU. Now, on a thermal analysis, you can have your thermal unit in BTU, or you can take it back into more native units, the more base units. And that's what we're doing. We're not using the BTU. We're using Q as pound force inch second, and it does work out. And that way your K, your thermal conductivity, and your specific heat then work out through that. Now, you can run a BTU or you can run it in base. It's a wash. It doesn't change anything because the thermals, since the K and the CP interact, just so long you have it right there, you're good to go. Okay. Here's our example. We're going to take just a section of that thrust collar. We're going to cut it down. We're going to give it a spot here. We're saying 1,000 degrees F, and we're just going to ramp it up in the first second, and it just starts cooking. And up here is some more stuff on units, and then from there, here's our checklist for the thermal. You got to have to, for your transient thermal, you got to have K and CP. You got to have a time function. Thermal load. No, you know, here you got to set the initial, and you got to set the transient for a transient thermal analysis. This is all in the base package. And then your analysis type is transient heat transfer. And we're going to run it for 600 time steps. Our time increment is 1, and it's unitless. We could have had fortnights or fortnights on instead of a time unit. But since our consistent unit system is based on seconds, this implies 1 second. I'll put intervals 20, So why don't I'll just bring up the model. Back up, models, transient thermal. And I made a start and a finish because this thing got a little out of control. Okay. Transient torch. Oh, interesting. Load definition. Unity load because it's scaled by that, by function. So I did make it. We're going to make an initial. Because we're heating it up. And nodal, select all. And just because I can, I'm going to make this at room temperature 70 like that. Okay. Control Q, because that's a little messy. And I can just do all off like that. And that. And now I have a constraint set. Now that's for later on. That's for the thermal stress. So let's go in and manage new. And it's going to be a transient heat transfer. I'm not going to give it a name. I'm going to keep moving. And page through these. Don't need this. Don't need that. This is the page I'm referring to. This is where you set it. 601. And output in 20. So we're going to have 30 sets being run on it. Max iterations. And then you're going to go ahead. See, it doesn't allow you to constrain. It knows that. Transient, initial conditions right there, initial temperature. And to cut down on the amount of data that it writes out, I'm just setting it to temperature. Now you could do spike functions. Now, one of the things that come up is that the loads can be a little tricky. Is that, for example, what if you have a temperature on this torch where, see, it's already run. Yeah, is where, you know, you're hitting it with the torch and then you turn the torch off. Well, if you do it as a temperature, you know you're going to ramp it up and ramp it off, but that's an enforced temperature. Enforced. That means when you ramp it down, you're going to be pulling the structure down with that temperature, which is not so good. So the way that you work it is that, well, the way we did it is that you can use a film coefficient. Think of the film coefficient as a pipe. And so you can open up the pipe or choke it back. And so we used the film coefficient to ramp the temperature. You know, you just have the temperature go up, film coefficient full, and then when we wanted to turn off the temperature, we just turned off the film coefficient. And it's like, think of it like a floating boundary then. So that worked out real well. So now we have our temperatures that came up like here, like that. And this is one of the nice things that you can do in an analysis study. It brings it all here. And you can animate the study. But first you have to tell it what you want to. And no, I don't. You got to go to post data. You got to tell it that you want temperature. Now what's this? You can one click and animate study. What do you mean? No data available for post-processing. Oh, well, fine, be that way. Temperature, fine. Oh, well.
And if you go to F5, you can pick an animation without deformation.
Down here.
Yeah, and then click that, and then down below you can skip deformation.
Skip deformation. There we go, thanks. We are so excited about this new feature in V12. We did it with the stress set. We didn't, you know, it's like, I'm going live now. I'm going off script. Oh, yeah. So anyway, this is what happened. Okay, fine. So anyway, you guys know that. So you get the temperature. Now, this is one of the conundrums with a transient heat transfer analysis is that you want to do a stress analysis to find out what the maximum stress is. And you got 30 result sets, and oh geez, old school. You know, you try to find you pick 2 temperature points and you plot the delta and you look for the maximum delta because the maximum delta will give you maximum stress. Ugh. So we had this project. We said, oh, we got to just do it. We just want to do brute force. We want to do it all. So what we did is, I shouldn't say we, Adrian did, he wrote an API. That this API will go through. It'll prompt you. I'll just run it. It's just so cool. No. I feel like you should be driving on this one, but anyway.
Oh, you got it.
I got it here. I got it here. I
Yeah.
haven't screwed it up yet. So, and this API it'll be on our website, and it'll also be. Oh, I got it. Go. API retransient. I got to go a little late. Thanks. There it is in all its glory. And you need to put some ASCII characters here with our name spelled out on the file. A little more sexier. So we'll just run it. So it asks for the sets you want to convert, and we're going to do all like that. And then it's going to pick one. It only wants to use one constraint set. And I think the more veteran Nastran users know where this is going to end up. So what it does is creates 30 thermal load sets for you, which is much faster. I mean, I actually, the old school method is you have to go to model, load, and now this is for your active load set from output. This is the old school way without the API. Oh, I should back up. I just did undo, so remove that. So if you had to do it old school, right? What's this? New load, thermal load at 600. That's active. You can imagine this gives a lot of picking from output. You want temperatures. And then you're going to, case one, you got to pick your temperature at 600, and then you do your factor of temperature. Voila. That was fun. And then you take that, and then you go into manage, new, it's a static stress analysis, right? And boundary conditions. That's one. That's one. So now, I mean, what do you do if you have 400? Oh, geez. You wear out your poor little fingers picking. So, yeah, I've done enough of that. So anyway, let's go back to the API. There we go. Select them all. Grab that constraint set. Run, baby, run. So there's our 600, but this is the cool part. That's an analysis guy. This is, and now I'm going to go ahead and delete the results since I don't need the thermal anymore. They're done because I got them all in the load sets. Now, I'll delete this. This is a little from the prior. So what's this? Oh, undo. Thank God for undo. Activate it. So this is it also creates your analysis set. Now you, the Nastran girls, know exactly why you want one constraint set. Because you only decompose the matrix once, because it's constraint set, you know, you first you arm it up, you calculate all the stiffness terms, you apply your constraint set, and then to generate your stress results, you're just applying different loads. And this is very old school. So now when you go and analyze it, it's only decomposing once. And then it's just like boom, 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 generating results from that. Look how fast it goes. I think it's 1001, Mississippi 2, Mississippi 3. Should be done. There we go. Takes more time to read in. And there's our 31 result sets through there. And those are all those are all your stresses for the thermal translation. And come on, there we go. Now it's a little rough because I had to really cut down the mesh. It wouldn't be a thing. Now I can go in here and I can go animate study. I can minimize this. That is bitching. That I just like, I first saw that animate study go, that is just awesome. So, okay. Now, now you want to say, well, which actual result set has the highest stress? And before we would, oh, that's the old learning thing. We would crawl through each one and sort of suffer with it, but watch what you do here. Envelope study, max value. It goes through, calculates the max value, stores it, for each, it's sort of, a running tally. It just searches through each set, finds the max, stores it. It's been there in the prior version of Femap, but you had to go up, and it also was deadly slow. Now it's a lot faster. There it is. There's your max stress in the structure, right there. Done.
George, you gotta run through that process one more time.
Yeah.
There was a little bit of lag on the screen. Just show people where to click.
Yeah. Interesting. Okay. Okay. So where that click is, there's two ways to get there. So here's your analysis study, which allows, you right-click on under analysis study, and you can envelope study max value. Now, this is the shortcut. Old school way was model, output, process. And then you could go to envelope, max value, select outputs to process. Yeah, it's a little cumbersome. And this is just sweet. You just go right there, max value.
So for any of the users out there that don't see this analysis study, it is a new thing for 11.2. So once you get up to date, you get that easier access to the post-processing.
Yeah, I tell you, there's so much stuff in here. It's a little bit, in 11.2, it's daunting. I haven't gotten to it. We've been using the beta, and it's just so much post data. There we go. I did a bunch of undo. So, okay, that takes us to the end of our transient thermal with the API, post-processing on transient thermal results. And this is my comment. There are many tribal mythologies that may be advocated, or one can use the brute force approach. I mean, it seems, hard-won knowledge. People cling on to it. Oh, this is the best way. Well, that's why we got computers. Brute force. We'll just grab it all. Look at it all. So, and I think we're on time. Oh, we're perfect. I'm trying to think these, make them a little shorter. Exactly that. And that is it for our presentation.
One note, I think the API, I think it was actually Nate that started that one, Nate Anderson. It might have been a little bit of collaboration, but in the blur of programming, I think he was the one that architect on that one.
Blur that did that?
I don't want to steal credit for his hard work.
I know what you mean. Hey, look at that! It's right there. He did do it. Damn. Okay, Nate, if you're listening, sorry.
I may have tweaked it, but I think it's his baby.
He's out of the office today, so yeah, I'll have him updated. I tell you, that was one bitchin' API, and it's not that big. This is one of the things we love about Femap. It's like, look, it's not that big. He said, if you need to go somewhere, the program can't get there immediately, you just write an API, and it can get there. And it's really about just cobbling other programs together. And we're happy to point you in a direction and throw some code at you. Here, look at this. You can parle this. Yeah. So I'm not going to get into 11.2. Adrian's going to do a special seminar on that because it's just there's so much stuff on it. There's just huge stuff on surfacing. I mean, Femap is getting so big on surfacing stuff that we're thinking about doing just a one-day training course in Portland, just on surfacing. And I'm thinking of tying it in with dynamics. I've loved dynamics, linear dynamics and nonlinear, but to do a NX Nastran linear dynamics class, 3 days, normal modes, sine suite, modal, response, PSD. And I want to end it with PSD fatigue because that's really where everyone wants to go. Is you run PSD and then you want to know about the fatigue life. So I want to get on that too, and then do a 4th day of surfacing. Have a class, just master class on surfacing, and get into 11.2. So if that sounds interesting to any of you guys out there, ping us an email. We're thinking of doing it at the end of June. I know it's a tough time. Kids are getting out of school. People want to go on vacations, but I don't know. It just seems like Portland's rainier than you can all get out, but well, what the heck. Any other comments? Close it up.
No, there's only a couple questions on here, and I think I got those covered, and either that or they were covered as you carried on with the presentation. So I think we're set.
Good. This thing will get posted early next week because it's Easter. I'm taking off. So to everybody, wishing you a happy Easter, and I'm shutting this thing down.